Okay, what we're going to do is take a look at the next unit, and this unit is referred to as stoichiometry. Don't worry too much about what the word stoichiometry means. Basically, it just means that you're using mathematics and balanced chemical equations to determine different values. So what we're going to do is use balanced equations and our dimensional analysis to solve math problems in chemistry. And it is a very logical process. You've just got to follow a couple rules, as with everything in chemistry. So anyway, the first thing you've got to be able to do is write chemical reactions. So if you're unfamiliar with writing formulas or writing reactions, you're going to want to go back and review that section. So let's write the chemical reaction for sodium oxide reacting with aluminum bromide. We've got sodium oxide reacts with aluminum bromide, and that's going to form aluminum oxide and sodium bromide. The next thing we want to do is balance this equation. So I can see we're going to have a little bit of issues with balancing, so I'm going to balance this one first. I'm going to put a 6 there, I'm going to put a 3 there, and everything balances. Alright, well, what we're going to focus on in stoichiometry are the coefficients. These coefficients are the numbers that come before the compounds in the balanced chemical equation. So our coefficients here are 3, 2, 1, and 6. If there's no coefficient written there, remember, it's implied that it's a 1. What these coefficients are going to do are give us ratios of the compounds to each other in the equation. And more specifically, usually they represent mole ratios. So what this means is if you're looking at this chemical equation, the mole ratio between sodium oxide and aluminum bromide would be 3 to 2. So if you were to start with a certain number of moles of sodium oxide, there's a ratio for every 3 moles of sodium oxide that react, 2 moles of aluminum bromide would react. Or for every 3 moles of sodium oxide that react, 6 moles of sodium bromide would be formed, or 1 mole of aluminum oxide would be formed. So these coefficients give you the ratio of how things react and how things are formed in the chemical reaction. Okay, let's take a look at some specifics with mole ratios. Okay, we've got our formula here, which we just balanced. We've got sodium oxide and aluminum bromide, sodium bromide and aluminum oxide. When we talk about mole ratios, these coefficients are going to represent a few things. They can represent molecules, they can represent moles, which we already said. If there's single atoms present, in other words, we said iron reacts with copper to form whatever, it would represent atoms. And it can also represent volume. If you remember the conversion, 1 mole is equivalent to 22.4 liters at STP. These coefficients can represent liters also. And this will become more apparent as we're working through these problems. So again, the coefficients can represent atoms, they can represent molecules. In other words, you can say 3 molecules of sodium oxide react with 2 molecules of aluminum bromide. And they represent volume. Now with mass, what we're going to do is convert from moles to mass. So these coefficients do not represent strictly mass. They can represent atoms, molecules, volume, and of course moles. So which of these are conserved? And remember, conserved means that whatever you start with, you have to end with. Total atoms are always conserved because mass is conserved. We know that already. My pen's not working. There we go. Numbers of molecules are not necessarily conserved because over here you can see we have 5 molecules create 7 molecules. And the reason these numbers can be different are because of molar masses. And we'll talk about that in a little bit more detail later. Volume is not conserved because, again, you could have 5 liters creating 7 liters. So the only thing that is conserved are total atoms, mass is conserved, and that's it. And then again, we will talk about this in more detail as we move through the unit. All right, then let's do some problems. Okay. The problem says if you start with 0.345 moles of sodium oxide, how many moles of aluminum bromide or aluminum oxide would be formed? Okay, what we're going to do here is do what we did with previous problems. Start with the given. So we've got 0.345 moles of sodium oxide. So what we want to do is we want to start with sodium oxide and calculate how much aluminum oxide will be formed. And what you'll see is I'll set up these problems the same way just about every time. I'll start with the given value. I'll draw an arrow from the value that I'm trying to get to the one I'm trying to find. And then what I'm going to do is write the unit of the one I'm trying to find underneath it. It's just a visual reminder as to what I'm trying to calculate. Okay, the first thing I'm going to do is set up a conversion. Now, since I have moles of sodium oxide, I know from previous lessons on dimensional analysis, I'm going to start with moles of sodium oxide in the denominator. And what I want to do is go from this to this. So what we can do is we write what's called a mole ratio. And the mole ratio is the ratio of moles of sodium oxide to moles of aluminum oxide. And that ratio is that coefficient ratio. So we have 3 moles sodium oxide and 1 mole of aluminum oxide. We get those numbers in the conversion from the numbers in the chemical reaction. So this way moles of sodium oxide cancel. The unit left over is moles of aluminum oxide. So if we take 0.345 divided by 3, we get 0.115 moles of aluminum oxide. So that would be our answer. Okay, if we started with 1.45 moles of aluminum bromide, so now we're starting with our aluminum bromide, and we want to know how many moles of sodium bromide would be produced. So we're going from here to here, and we're trying to find moles. So let's do the same thing. Let's start with 1.45 moles of aluminum bromide. Let's set up our first conversion, and again, whatever we're starting with goes in the denominator, so moles aluminum bromide. Now what we want to do is go from aluminum bromide to sodium bromide. So we're going to do a mole ratio, and again, the mole ratio is the moles of the thing we are trying to get rid of to the thing we are trying to get to. So let's cancel out our moles of aluminum bromide, and what's left are moles of sodium bromide. So let's do the math. 1.45 times 6 divided by 2 gives us 4.35 moles of sodium bromide, and that would be our answer. Let's just do 2 more quick problems. Okay, if you started with 0.85 moles of sodium oxide, so we're starting with 0.85 moles sodium oxide, and we want to find moles of aluminum bromide that react, we can do that too. In other words, in the previous problem, we started with a reactant and found a product. Well, now, all we're doing is starting with a reactant and calculating another reactant. So we're going to start with 0.85 moles sodium oxide. Again, conversion, what we start with always goes in the denominator. What we're trying to find in terms of moles goes in the numerator. I've got to work on my handwriting with this thing. The numbers are the coefficients, so 3 and 2, and we're trying to find moles, so we can stop there. Those cancel. 0.85 0.85 times 2 divided by 3 gets us 0.567 moles of aluminum bromide. Let's do the last one. We're going to start with 1.345 moles of sodium bromide, and now we're trying to find moles of aluminum oxide. So we can go from sodium bromide to aluminum oxide. So what we have here is a situation. Sorry, my cat just jumped on my computer. So what we can do is it shows that if we start with one product, we can simply calculate another product. The point of this is that whatever we start with in the equation, we can calculate any other value. It doesn't have to be reactant to product or reactant to reactant. It can be any combination of two. So let's put moles of sodium bromide in the denominator, and we're going to moles of aluminum oxide. Numbers from the reaction: 6 moles sodium bromide, 1 mole aluminum oxide. 1.345 divided by 6 gives us 0.224 moles of aluminum oxide. That's supposed to say aluminum oxide. Okay. So again, just to recap, we write a balanced equation. The coefficients that balance the equation represent either moles, molecules, or liters. And we'll do problems with all of these in upcoming podcasts.